Work is a scalar quantity, so its SI unit will be joule. But when the work done by the applied force is the product of the horizontal component force and displacement, it will be work equal to Fs cos theta. So we will see the example. Example is a boy pulls a 10 kg block 30 meter along a horizontal surface with 120 Newton horizontal force. The coefficient of the friction between the block and the surface is 0.2. So first we need to find work done by the applied force. So we use the formula is work equal to force times S. It will be 120 times 30 and we will get 3600 joule. And second one is we need to find work done by friction force. So first we need to find friction force. So friction equal to mu n, so it will be 0.2 times 100, and so we will get 20. And then we need to find work done, so it will be 20 times 30. We will get negative 600 joule because it's friction force. So the third one is we need to find the total work by all forces. So we will get work applied plus work force. So we will get 3,600 minus 600 joules. So we will get 3,000 joules. We're going to talk about energy. Energy is ability to do work. Energy can be stored or transferred from place to place or object to object in different ways. The first one is kinetic energy. Kinetic energy is due to motion, so its equation will be Ke equal to 1/2mv squared. And for work done, it will be delta Ke or Ke final minus Ke initial. So we look at the example. A car mass is 2,000 kg moving at a speed of 20 meters per second and slow down uniformly to a speed of 10 meters per second in 4 seconds. So we need to find initial Ke. So we use the formula 1/2mv squared. It will be 1/2 times 2,000, and V initial is 20. So we will get initial Ke, and then the final Ke. So we will use the same formula is 1/2 times 2,000. But the final is 10. So we will get 10 is V, and then we will get final Ke. And we need to find work done. So work done, we use the formula is delta Ke. So Ke final is equal to this one minus with initial Ke. So we will get the answer for work done. And for potential energy is due to its position. And gravitational potential energy is a stored energy due to height from the ground, as you see in the picture. So its formula will be Pe equal to mass times G times H, and its SI unit will be joule. And this one is work done by elastic force. When a force is exerted on a spring, it stretches at a displacement x. In Hooke's law, the formula will be F equal to Kx. The spring force is variable force. So for work done will be equal to 1/2 times K times x squared. In this example, it said that 2 kg object released from a height of 4 meters on an inclined plane, as shown in the figure. If the spring constant is 200 Newton per meter, by how much the spring is compressed by the object. So this one need to find x. So in this this example, we use two formula is PE equal to EP. So the formula for PE is mgh, and for EP is 1/2 kx squared. So for m, we know it is 2, and g is 10, and for height it is 4. Equal to 1/2. For this, k equal to 200, and we don't know x. So we find the x. X squared. So x squared is equal to 0.8. So x will be 5/5. So for the last topic is power. Power is a rate at which work is performed by a force. So power equal to W/T, and it can be F times S/T and FB. So SI unit for power is joule per second.
Hello, my name is Napasorn Phongpitchayapisut from M5A number 15, and today I'm going to talk about circular motion. Circular motion is the motion of an object on a circular trajectory. We will talk about this one first. Angular displacement. It is the angle turned by the object. The formula is angular displacement equals to S/R. S is the arc length and R is the radius of the circular path, and the SI unit is radian. The next one, the angular velocity. It describes how fast an object rotates about an axis. We use this one as the symbol. This one called omega, and this one is zeta. The formula is angular velocity equals to angular displacement over time, and the SI unit is radian per second. The angular displacement can be measured in degree, revolution, or radian. One revolution equals to 360 degrees equals to 2 pi radian. Let's see an example. This one is solved by me. Convert 2/3 revolution in radian. We know that 1 revolution equals to 2 pi radian. So what is 2/3 revolution? Equals to x radian. And this time 2 pi with 2/3, and we got 4 pi/3 radian. Another example. A wheel makes 180 revolution in 0.3 minutes. Calculate the angular velocity in radian per second. First, we have to write given. The zeta is equal to 180 revolution, and time is 0.3 minutes. They want to know what is the angular velocity. We use this formula, but first we have to change revolution to radian by this one. Just time 2 pi, and we got 360 pi radian. And we use this formula. We have to change 0.3 minutes to 2 seconds, so we time 60, and we got this answer, 20 pi radian per second. The next one motion is equal to omega r. Tangential velocity is when a body is moving in circular path, there is a tangential velocity. The SI unit is meter per second. The next one is angular acceleration. We use this one is alpha as the symbol. It is the change in angular velocity. This is the formula. It also same as the linear motion but change the symbol. The next one, tangential acceleration. It is the change in tangential velocity. It also same as the angular acceleration but not the same as the symbol. The SI unit is meter per second square. This is the relation between linear motion and circular motion. It is the equation of linear motion and circular motion to show that it's quite similar, but we just change S to zeta, change A to alpha, and change V to omega. Let's see an example. A disc initially at rest rotates with constant angular acceleration through an angle of 50 radian in 5 seconds. Find the angular speed of the disc just after 3 seconds. So first we have to write given. The initial angular velocity is at rest, so it is 0. And zeta is 50 radian, time is 5 seconds. And they want to know the angular speed of the disc after 3 seconds. First we have to find alpha, or the angular acceleration. So we use this formula and we got 4 radian per second square. And we find angular speed by use this formula and we got 12. The next one, the centripetal acceleration. It is the acceleration which arises due to the change in the direction of the velocity. This is the formula. Centripetal acceleration is equal to v squared over r equals to omega squared r. And the next one is centripetal force. It is the net force required to keep an object moving on a circular path. The formula is centripetal force equal to mass time centripetal acceleration equals to mass time v squared over r. Or we can use mass time omega squared r, because from this one it's related. So let's see the last example. Find the centripetal acceleration of a 2 kilogram object that rotates with 13 revolutions per second on a circle with a radius of 15 centimeters. What is the centripetal force? First we write given. They want to know what is the centripetal acceleration. radius is 15 centimeter, and they want to know centripetal force. So first we have to change revolution to radian. So we just time 2 pi and we got 26 pi radian. And we have to find the centripetal acceleration. So we use this formula. Centripetal acceleration equal to omega squared r. And we got 101.4 pi square radian per sec square. And then we find the centripetal force by use this formula, mass times centripetal acceleration. So we got 202.4 pi square Newton. The unit of force is Newton. Thank you.
Morning, my name is Eunjoo and I'm from 5A number 24. Today I will explain about rotational dynamics. When an object moves in a straight line, then the motion is considered as translational. But when the same object moves along an axis in a circular path, it's called rotational motion. For example, a wheel rolling without slipping in a straight line. The forward displacement of the wheel is equal to the linear displacement of a point fixed in the rim. In rotational motion, the object is not treated as a particle but is treated in translational motion. The rotational dynamics starts with the study of torque that causes angular accelerations of objects. To understand the rotational dynamics, we need to know about many terms like torque, angular acceleration, and etc. Angular displacement is denoted by theta. For a particle moving in a circle of radius r and assuming that it has moved in arc length of s, the angular position theta is given by theta equals to s over r. The unit is radians. 1 radians equals to 180 over pi. The angular displacement can be defined as the change in the angular position of the particle or object. There are 3 rotational dynamics equations. They are Wt equals to Wo plus At, Qt equals to Qo plus Wot plus 1 over 2 At square, and Wo equals to Wo square plus 2A times Q minus Qo, where Wo is the magnitude of the initial angular velocity, Wt is angular velocity's magnitude after time t, and Qo is initial angular position, and Qt is angular position after time t. Next is the conservation of rotational energy. The law of conservation of rotational energy states that the energy of a system remains constant. Energy can neither be destroyed nor be created. It changes from one state to another. For rotational energy, energy equals to kinetic energy plus potential energy, or mgh equals to 1 over 2 mv square plus 1 over 2 mw square. The units of rotational kinetic energy is joules for SI system. Next is torque. Torque can be defined in various ways. Torque is the turning effect of the force about the axis of rotation. The number 2, the moment of force, is also called torque. Torque is positive for a force that causes or tends to cause counterclockwise rotation and vice versa. The rate at which there is a change in angular momentum is also called torque. Any force whose line of action is not directed towards the axis of rotation or the center of mass for an object will provide a torque on that object. So the torque is perpendicular distance from the axis of rotation times force. So T equals to R times F. R is the distance between the point from which torque is measured to the point where force is applied. T is the torque and F is the force applied. Its dimensional formula is ml squared T minus square, which is same as that of work. Next is center of mass. The center of mass is an imaginary point where one can assume the entire mass of the given system or object to be located. Characteristics of center of mass are: number 1, the point can be real or imaginary. Example, in case of a hollow or empty box, the mass is physically not located at the center of mass point. Number 2, this mass is supposed to be located at the center of mass in order to simplify calculations. The motion of the center of mass characterizes the motion of entire object. Number 4, the center of object. Number 4, the center of mass may or may not be the same to the geometric center if a rigid body is considered. Number 5, it is considered as a reference point for many other calculations of mechanics. For example, a disk is rotating with a constant angular acceleration of p radian s square about a fixed perpendicular axis which is passing through its center. Find the angular velocity of the disk after 4 seconds. B. Find the angular displacement of the disk after 4 seconds. C. Find the number of turns accomplished by the disk in 4 seconds. Solution is W is 4 seconds equals WO plus AT. So 0 plus P radius second square times 4 seconds equals to 4 P radius per second. The angular velocity is 90 plus Q plus WOT plus 1 over 2 AT square. So 0 plus 1 over 2 P radius per second square times 16 seconds square, it equals to 8 P radian. Let the number of turns be n, then n times 2 P radians equals to 8 P radians and n equals to 4.
Hi everyone, in this video I will be talking about Newton's law of universal gravitation. So let's get started. Newton's law of universal gravitation states that every particle attracts every other particles in the universe. So how does that work? Well, take a look in the diagram. There are two objects with masses positioned in a distance r. Even the distance is infinite, or the masses of two objects is very little in the micro unit. As the Newton's law stated, there is still gravitational force. Now let's get to see the equation. The gravitational force equals to the universal gravitational constant, which we use as the capitalized G to represent it in the equation, times with the mass of object 1 times with the mass of object 2, all together divided by the distance between centers of mass of these two objects square. And as the universal gravitation constant is a constant by its name, it has a value of 6.674 times 10 to the power of negative 11. And here is what you must concern about this using this equation. First, the unit of the masses, it must be in kilogram. So, if what you are using is gram, then you must convert it into kilogram. And second, the letter R does not mean the radius of any object, but is defined as the distance between the centers of mass of the two objects, and it sometimes works out to be the radius, so you must pay full attention to that. Okay, so now let's talk about some Newtonian physics, and it explained that the gravitational force is also equal to the weight of a body. So what is the equation of gravitational force? Well, it is Gm1 times m2 over r squared, and the weight is m, the mass of any object, times with g. Well, g is gravitational acceleration, which on Earth is equal to 9.8 meter per second square. Now just let's assume that m1 equals to the mass of the Earth and m2 is equal to the mass of the object. So the weight must be the mass of the object times with the gravitational acceleration. Let's find the equation for gravitational acceleration. So now we know that this can be cancelled out and the only remaining side is g, so we can rewrite this equation down into g equals universal gravitational constant times with the mass, now assume the Earth, over r squared. Now let's come to the orbital velocity. So we know that the force of the gravity is equal to the force, the centripetal force, as it acts the same way as how circular motion works. And so thus we can bring these two to equal one another. Now we can simplify this equation by cancelling out the distance and the mass, and this v right here will be the orbital velocity of the object that orbits the more massive object like Earth. Now we get that the orbital velocity equals to the square root of g of the big G times with the mass divided by the distance. And keep in mind, this distance isn't the radius, but the distance between centers of mass of the two objects. So in case of the Earth, we can say that we can rewrite this equation into the big G times with the mass of the Earth divided by the radius of the Earth times with the altitude of the satellite orbiting it. And we can also bring this equation to pi r over t from the circular motion. Keep in mind that the radius of the Earth equals to 6.4 times 10 to the power of 6 meters. There are two things that make a satellite orbit. They are acceleration towards the more massive object and the velocity of the satellite orbiting, which they are tangential to one another, and that those two values stay the same. Assuming that that the eccentricity equals to 0, which defines that the orbit is perfectly circular. The direction of these two things will always change according to its position. That's why the satellite orbits. Gravitational potential at a location is equal to the work per unit mass that would be done by the force of gravity if an object were moved from its location in space to a fixed reference location. And simply, it is the work done in bringing a mass from infinity to that point where the mass is, because the equation only consists of one mass. So here's the equation. Is phi equals to negative capitalized G times with a mass divided by r, the distance. Don't forget that the r is not squared in this equation. Now let's come to gravitational potential energy, or GPE. Well, I think that everyone have heard it, where gravitational potential energy equals to the mass, the gravitational acceleration times with height, or the distance. But this one is not we are talking about. We are talking about gravitational potential energy, where it equals to negative capitalized G times with mass 1 times with mass 2 divided by the distance r. But what's the difference between them, these two equations? Well, the gravitational potential energy, where it equals to mgh, is used in where the gravitational field is constant. For example, the surface of the Earth, where g is a constant. But the equation for what we are talking about is the energy where the gravitational field is not constant. For example, when the distance is infinity. Now let's talk about kinetic energy. Usually kinetic energy equals to 1/2 mv squared. So in this topic we can change the velocity to the orbital velocity, which I have explained